Hey, welcome to Language-Based Security on Androids. This presentation is presented by Ritesh Verle for Giddy Kermai, section 4377.001. Welcome to the introduction section of the presentation. The article I read was called Language-Based Security on Androids, and it was created by Avik Chaudhuri. There are a lot of consumer and producer problems to this day. For example, say you need to download an app or you see an app being advertised. You download it and open it, yet when you're going through the terms and conditions, you just accept everything. For example, say if you downloaded Instagram and exactly when you wanted to upload a picture, it asks for your permissions to go inside your gallery so you can get the picture. And you allow Instagram to that permission. This is going to be a big problem. This gives Instagram all permissions to your gallery. Now, this brings concerns for the consumers, and it also brings concerns for the producers. If the consumer cannot trust in the producer's product, then the consumer won't buy the product. Now, how will there be a way to guarantee safety for the consumers and producers? This will be addressed throughout the presentation. We will first understand the overview of Androids, and then we'll start going into languages regarding Androids. We'll understand the syntax, local and global reductions, and we'll even go into semantics and type systems. Now for the overview of an Android. First, I feel like it's important for us to understand the overview and what goes behind Android security before we talk about language-based security regarding the Android. There is one thing called the application model. An application is a package of components, each of which can be insustained and run as necessary. There are 4 types of components for the application model: the activity, service, receiver, and provider. Now, for these 4 components, there's also classes and methods regarding these 4 components. The activity class has methods that will run when some activity calls this method. The service class has a method that is run when some components binds to the service. The receiver class has method that is run when a message is sent to this receiver. And then the provider class has methods to query and update to the data stored by its provider. So as you can tell, I'm pretty sure that the activity and receiver are probably one of the most important classes regarding language-based security, considering that if I were to accept Instagram to use my camera, for example, then the activity will make it so that Instagram can always use my camera. And that is a big security problem, considering that each time I open my camera, Instagram could see and access anything that's going on. Now we're at the program syntax part of the presentation. This part of the presentation is absolutely imperative to understand, considering that this will be the base fundamentals throughout Avik's language. We have V, which equals value, I equaling the intent, and then T equaling the code. We can call an activity, we can return from activity, bind to the service, register a new receiver, send to a receiver, read from the provider, write to the provider, evaluate, fork, choice, and have a result. These are all extremely imperative, considering how we will be using this to guarantee security in Androids. We are now at the application syntax of the presentation. A program runs with a permission. This is very common sense. If you were to look or download any application, you would be signing off on agreements for you to download the application in the first place. In order for you to download an application in the first place, you have to allow permissions for your phone to download it. In general, the program may run on a stack of windows produced by the calls to activities or in a pool of threads. To the left-hand side, we have a diagram, which is all about the application syntax. We have the definition, we have the activity, which has parameters, calls, and permissions. Along, we have service, receiver, provider, and a hash of definitions. Now, the program syntax and the application syntax do differ. The program syntax will be done more locally, while the application syntax will be done more globally. Welcome to the part of the presentation that will go over local and global reductions. First, we will begin with a global reduction. A global reduction describes the reduction of states. This relation depends on local reductions that describe the reduction of expressions under an environment and a pool of threads. On the left-hand side, we are given local reductions. We are given functions and expressions that will describe these local reductions. We are given a let distribution, let evaluation, return, fork, read and write, and then register. These are extremely important, considering how register will always let us register where the user is currently in. Read will be able to, of course, read, and write will be able to write. Then we have even more in local reductions. We have send, choice, and choicer. Now, if we go over the global reduction, we have a more simpler but also imperative part of the reductions. We have local, call, return, and thread. Just as you would expect from any local and global states, global allows for one local variable. It will call, return, and thread some functions that were either put down in local or are still global. We are at another imperative part of the presentation, which are semantics. In programming language theory, semantics is the field concerned with rigorous mathematical studies of the meaning of the programming languages. So, the article goes on to introduce internal semantic categories to describe intermediate states of an android. An expression denotes code running with a particular expression. A thread is simply an expression. Now that we know both, we can understand what a window is. If you look at the bottom left-hand section, we will see the formula or form of a window, which is E lambda x dot E prime. E is the expression in the form of the window, and lambda x dot E is the callback that will be invoked. As a state is a tuple, we're given variables D, S, and E, where D is an environment, S is the stack of windows, and E is the pool of threads. Now we are at the type system part of the presentation. We will begin to present a system of security types for our language. The any read write is given to data that may flow from context, which at most permission write to contexts with at least permission read. Now, this may be a little confusing, but pretty much what this is saying is, in order to get permission to write, we must have permissions to read. And this is very imperative. We will go on to understand the variables that were given to us by a VIC. We're given a T, which is a data type. Think of it maybe as generic. Then we have the any function, activity, receiver, provider, and stuck. Then big T is of type. And we're given two types, data type and stack type. In the previous slide, we went over the type system. It's important for us to go over the typing rules now. Let T be a list that associates names and variables to unique typing and hypotheses such as N to T or X to T, where T, again, would be a generic type. There is a subtyping rule that captures safe data flows. Now we're starting to really understand where this whole presentation is going to. our overall main formula would be the subtyping rule that captures safe data flow. If we're able to somehow find a way to capture safe data flow, we should be able to properly secure security for the consumer. We are given the exact type on the left-hand side and the subtype on the right-hand side. So the left-hand side has write, read, register, send, let, fork, choice, value, hype, value, void, call, and return. And then the sub-hand side has any. There are a couple properties of typing. The main theorem is following data flow security property for any sequence of reductions of a well-typed state. A well-typed state was just previously mentioned in the typing rules section of the presentation. It was the left-hand side of the diagram. This theory guarantees that a value can flow from a provider into a provider n prime, only if readers of n prime may already read n, and writers of n may already write n prime. The theorem follows from a standard subject reduction lemma. The main theorem works well for only well-typed states. In practice, though, this requirement may be too strict. We may want to consider the possibility of safely running an application even if it does not type check. This is really important. There's some times where we might want to run an application where we aren't using the well-typed states. And exactly how would we do this? We should be able to do this with the new variable we are given, which we will call t for now. But it is pointed out by Avik that t does not necessarily equate to no permissions at runtime. So even though we do not type check, we're also not exactly guaranteeing that there are no permissions that were allowed. So now we will go over the summary. We have discussed the introduction, which was the problem of language-based security, or what Avik really generalized the problem of language-based security to be. Then we went over the overview, which was mainly the application model, components, classes, and methods. Then we went over the program syntax, which was the syntax for Avik's own language. Then we went over the application syntax and how a program runs with a permission. Then we went over local and global reductions, which were followed by semantics. Then we went over type systems. And then now we were finally starting to get into how the consumer can get data safely, and how this typing rule will always allow the consumer to have security. But we had to go over the properties of typing. Then we went over untyped code, which follows to if we are given no type, then we need to have a variable to equate for this untype, which will equal no permissions. My critique is overall Avik did an excellent job. He created his own theory that can be used. Granted, if you felt overwhelmed during this presentation, that's kind of how I felt when I first read his article as well. Avik did a really good job, though, of constantly bringing in real-life situations regarding the Android throughout the whole article. The theories regarding his language made sense. There were parameters, there were arguments, there were call functions, there were basic syntax that we were able to build up our knowledge on for his own code that he made. Granted, I am more of do it yourself to understand, and I wish that there was a way that we can actually implement his theorems. But there is a lot of information that was thrown onto the reader, but everything was backed up with logic and claims that supported this information. Overall, I really did enjoy reading this article. So now we're at the conclusion. Throughout the article, Avik kept mentioning that there was a problem with consumers and producers. Towards the end, Avik's theory managed to solve the problem, though, of secrecy that made consumers not want to buy products from Androids for quite some time. Actually, in the example of typing rules, Avik manages to guarantee safety for the consumers. Avik successfully managed to notice a problem with language-based security regarding Androids, and he solved this problem. I want to thank you for listening to my presentation, and I hope you have a good day.